Hi. So I am not a programmer at all. I learned a little bit, enough to help me out with my research. I am a physics grad student at Portland State. It's actually been really encouraging, the number of physicists and physical science folks that have gotten into this field. And so what I want to talk to you about today is how I use machine learning for my research. So what I do is I study image sensors, and particularly I am looking for this kind of signal here. It's called random telegraph signal noise. It's where we have these discrete jumps from one state to another. This is so what I do is I take a bunch of pictures in a dark box, and then I stack all those pictures together, and I look at the pixel output from a single pixel, and that's how I get some sort of time series like this or digital signal from my device. And it's a convenient way to do device physics and silicon device physics in particular, because each pixel sort of acts like its own device, and I can operate on 10 million of them at the same time if I have a 10 megapixel camera. So this is what I'm interested in. There's some sort of atomic defect that switches back and forth, sort of ticks and talks between these two states. And so out of 10 million or so pixels, I want to find the pixels that just do this sort of thing and analyze them. So the way I want to do that is through signal reconstruction. And the reason I want to do that is because I want to just look at the amplitudes and these state lifetimes. So RTS amplitude is defined as this difference between the two means of the states, and the state lifetimes are the high and the low. These are the things that tell me physical information about what's happening inside the image sensor. So there's some unique challenges to this sort of work. In particular, older methods, but still state-of-the-art methods for 10, 15 years, struggled, and that is there is no well-defined limits for how short or how long an RTS pixel can stay in one state or another. And there's no real limit to how small the amplitude can be. So the amplitude can be very, very small and hidden in the noise. Additionally, like I said, maybe there's only 10,000 of these in an image array of 10 million pixels. So I turned to machine learning and created actually two models to help me do this. The first is a classification model, and it works very similar to image classification, but instead of doing 2D convolutions like we've seen a few times over the last couple days, I do one-dimensional convolutions. I trained a model to give me a 0 if it's an RTS pixel, something that's fun and interesting for me to look at, or a 1, or if it's a non-RTS pixel and I don't have to look at it. Additionally, I don't like all this noise going on. And when I say noise, I mean this is RTS noise, is the big transitions, but there's also Gaussian noise, or white noise, the stuff that is constant over both levels. And that stuff's not interesting at all. You can't get rid of it physically, so you have to get rid of it computationally. And so I used what's called a denoising auto-encoder. And so instead of sending in some signal that is size 1500 and getting a 1 or a 0 out, I get something back out which is the same size of what I put into it. And the autoencoder learns by creating gaps and then figuring out how to fill in those gaps in a sensible way so that my signal to noise increases quite a bit. From there, I can use some classical methods. I know what I'm looking for is two Gaussian sums. So I take a histogram of the autoencoder output, and I fit two Gaussian peaks to it, and then I tell it to scan through the signal again and say, whichever value you're closest to, one peak or the other, I insist that you go to that level and you stay there. And that way I get this nice, very square reconstruction of my signal without any white noise on top of it. And now it's in a form where I can collect these amplitudes and these state lifetimes very easily. To test it very, very quickly, I built another same sort of block that I created to train it, which is simulated signals. I use a correlation coefficient. This is another sort of picture of what that looks like. And here's the results. So the correlation is very, very high on everything except for small amplitudes, which is a nearly impossible task to do. And then I also trained it. This is actual real data that I took with a camera, so these are not simulated signals. It's more difficult to give a quantitative expression when you're talking about real data, but this is real actual data that I took from a real image sensor. And thank you for listening. This is my QR code for my website if you're looking for someone who wants to do signal processing. So.